Well, good morning, afternoon, or evening. I'm Professor Rios, and welcome to this week's video. This week we move on to ice sheets, sea ice, and glaciers. Probably one of the more obvious aspects of climate change besides temperature, because it's something that really can be seen. So the change in ice. Ice is not permanent. Ice changes all the time. Ice, when over water, is very subject to wind and currents and storms. So ice is constantly changing. Even the ice in Greenland or ice over Antarctica is not necessarily permanent. So do bear that in mind. Don't forget to go over the lesson material on the class page. This week is a little different, so please bear that in mind. There is a homework that is based on a documentary, so please do bear that in mind and make sure that you get to it. There is no forum, I believe, and there is also no quiz, but there's a homework, and that homework is a little bit more valuable in terms of points than usual. So having said all this, let's get going. Again, always make sure that you look at the announcements or any emails that have been sent, in addition to go over what the to-do list has for the particular week. So having said that, let's get started. This right here is a lake on top of ice that's been formed in Antarctica. It basically exhibits many of the patterns that a lake and a system of rivers feeding into a lake would do over land, except it happens to be over ice. So in other words, ice isn't permanent. It's not static. It's always changing. You may see this one lake this year, and this lake may not exist the following year. Okay? So basically, ice has been, or Greenland, for example, has been losing ice mass since at least 1990. And it's been very, very, with high confidence, losing at a highest rate between 2010 and 2019. Again, this is according to the IPCC AR6. Glaciers in all polar regions, but especially Greenland, have lost significant ice mass. And they have, remember, ice is like a big stabilizing force in the planet. So if you lose a lot of ice, it's sort of like losing the radiator in your car. So again, that's the source, working group 1, AR6, fact sheet of polar regions. So in terms of dynamics, and remember, the word dynamics simply implies what are the mechanics, the movement of ice. So ice usually accumulates at the center, and it basically slopes away from the center by gravity. Think of it as a big, big ball of silly putty. If you leave it on top of a desk for about a week and come back later, it will probably look more like a frisbee by the time you get back. It basically begins to move in all directions. And as a result, you get all kinds of activity happening over ice sheets. Ice sheets move like plastic. It's just one of those weird properties of ice when it begins to move under the force of gravity. Now, again, the Greenland ice sheet has been stable since about 10,000 years ago, but it is showing signs of anthropogenic, there's that word again, warming. If all of it were to melt, not likely, but if all of it were to melt, sea levels around the world would rise by about 7 meters or 21 feet. Again, highly unlikely. So at the interface between the ice and the water, meaning the ocean, you have what are called outlet glaciers. And these are basically rivers of water. Basically, think of the Hudson River as it empties into the Atlantic Ocean next to the lower New York City World Trade Center area. That is what an outlet glacier would be. Okay? Outlet glaciers and ice shelves basically tend to hold back ice. Think of yourself standing in a room where you're trying to keep the door locked, and you put your hand up against that door. When you do that, you are buttressing. That's what that word means. You're holding back the ice from the other side. And these are outlet glaciers. This is the southern tip of Greenland. And you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. You can count. There's literally hundreds of these in the southern end. This is the ice sheet itself. And these are the outlet glaciers. Notice how it goes from white to gray. So the ice here is thinner. This is what ice, notice how it looks like whipped cream or some sort of like cream that basically just spilled out and basically formed this very distinctive, sort of like an elephant's foot. This is an outlet glacier. There was an opening in the terrain between this mountain and this mountain, so there's a valley here. Notice the area of accumulation. Notice how much whiter it is. It is colder. And as you get further down or lower in elevation, notice how it becomes dirty, becomes gray, because it's basically carrying a lot of the material from the mountains that's been basically worn out by the force of the ice moving over it. All right. Here's another example. Again, the Greenland ice sheet. So this little square here would be this square, roughly. Petermann Glacier would be right there, that dot. That's this. Excuse me. And here's a sense of how it changes. So here's an image from 2016. 2017, 2019, and 2021. So that ice is advancing with time, and sometimes it cracks, and when it does, a big old iceberg will basically move towards the ocean. And then all that ice will be carried by currents. There are meltwater lakes. That would be that image at the very, very beginning of the lesson. They accumulate on top of the ice in summer, and they can drain away in just a few hours. These are not especially deep lakes. They may be anywhere between 10 and 60 feet in depth. But the water, basically, if the ice cracks, then it's like basically pulling the plug from a sink, and then the water just drains down, and it drains into the ice, destabilizing it further. Okay, so here's an example of another one. It's very pretty, very like almost like metallic blue. Here's the ocean in the distance. So this is ice that is very near the ocean, so it's on the edge. If you go any further in this direction, you're going to be going inland, and that ice becomes thicker and therefore taller or higher in elevation and colder, so it doesn't melt as easily. Here's another example up close, what that can look like. Ice sheets, so that's the idea of flow models. And we have to think about streams in the form of ice streams. So a recent discovery is the discovery of what's called the Grand Canyon of Greenland. So if you're somehow able to remove the ice from Greenland, like if you could magically just erase it and look at just the land, you would find that there's a canyon in the middle of Greenland that travels north towards basically the Arctic. It is deep, and it empties into what's the Petermann Glacier, that glacier we saw earlier in the lesson, and it has V-shaped mountains, meaning that that area was once not covered by ice, because you only find V-shaped glaciers, V-shaped profiles of land in areas that have no ice. Okay. So here's an example. So this would be basically Greenland without ice. A lot of it would be below sea level, so there might be lakes in the middle of it. And here's that canyon right there. Right there. That Grand Canyon would be roughly there. And there are mountains on the edges and a big, big valley in the middle. So that's Greenland without ice. And a little bit up close, there's the Grand Canyon of Greenland. And again, this image here would be roughly this, right there. And there it goes. And it follows all the way through into the ocean near Canada. So since 1979, there's been significant surface melting of ice over Greenland, where you find essentially more than 25 days of melting. And that may not seem like a lot, and that's because the melt season isn't especially long. It's usually between the months of basically June, July, and about early September, and that's it. So the rate has increased, and from 2010 to 2020, the melt rate has continued to be above that 1980 to 2010 average. So as a result, the entire surface of Greenland has turned darker, and that's because there's been a lot of dust and soot that has accumulated. Remember, dark particles attract and collect heat, right? That's why you don't wear black clothing in the middle of summer during a hot part of the day, because you will overheat. You wear light color clothing. You might wear black in winter because that will help you stay warm, right? So as a result of this increase in dust and soot, there's been an increase or an accelerating melting that's been taking place. And again, focus on the trend. Always look at trends. And this is the Greenland ice sheet mass loss from 2002 all the way to about 2022. So with a little bit of no data gap here in 2018, the bottom line trend is a decrease. Hopefully that's pretty obvious to see. So take the next difference here. When we talk about, you measure accumulation, how much you dump into a system, and take melting, how much you remove from the system. And the net difference between those two events is either a gain or a loss. If you gain, then your glaciers grow. If you lose, then your glaciers shrink and retract, okay? So the bottom line is, for Greenland, there's been a net increase near the center, but a net loss at the edges. So what that means is Greenland is getting steeper. That ice is becoming steeper because it's a bigger hump in the middle, so to speak. And here is the average. So in 1981, how many melt days were recorded? Between 0 and usually no more than about, that's at yellow orange, so roughly about 50 to 60. In 2001, notice how it's changed from 1981 to 2001. You see a lot more of the blue, you see more red, you see more orange up north. And by 2021, the difference is pretty significant. You only really have no melt days at the very, 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 very top of the glacier, or the ice sheet rather, where it's, 8, 9, 10,000 feet in elevation. So whereas all this used to be 0 days of melting, now it's only a very small area by comparison. And here is the data in table form since 1992. 2012 still ranks as the most significant year for loss of ice over Greenland. The trend here isn't as obvious I mean, there's definitely an increase from 1992 to 2012, and then it sort of has stabilized somewhat, but it hasn't gone, there hasn't been a decrease or a negative trend. And here's the idea of 2012 is the worst year of surface melt on record. That's what it looked like. Notice these colors. There isn't a single area of Iceland, or of Greenland rather, that is white. So even the highest area recorded some loss of ice. And here is 2012 versus the average versus 2022. So 2022 would be the blue line, 2012 would be the orange line, and the average would be the gray line. So that would be this line right about there. So notice how both 2012 and 2022 were significantly above the average. That's the takeaway. Again, comparing the average for 1979 to 2007, and again for the year 2012. Again, that's sort of a benchmark now. You know, that's the year that is now being, and that was 10 years ago already. But the fear is there's going to be a year in the not so distant future where 2012 is going to be beat as far as that record. Okay. So what happens with Greenland? So Greenland, when it melts a lot of ice, when a lot of ice melts from Greenland, better said, what happens is you're dumping a whole bunch of fresh water into the Atlantic Ocean. And when you dump a whole bunch of fresh water into the ocean, you're making the water less salty. And less salty water is less heavy water. The heaviest possible water is salty and cold. The lightest water is warm and fresh. And if you recall back to the very beginning of the term, that plays into the whole idea of the thermohaline circulation, which has to do with temperature and salinity. So when you dump a whole bunch of fresh water into an ocean that is salty, you are freshening that water system, making its density change. So it's a negative feedback that takes place, and let's get into that. So, and we'll get into that coming up. So let me go back to this real quick. So this whole thing here is a negative feedback, meaning warming leads to melting, and that means there is less heat in the North Atlantic Ocean, which then can cool Europe. Get it? Negative, counteracting, as opposed to a positive feedback, which is reinforcing. So let's look at this. So remember the idea of the Ice-Albedo positive feedback. So albedo is the percentage of light that's reflected. So ice is reflective, has a high albedo. It absorbs heat. It absorbs very little heat because a lot of it is reflected back. Open water is dark, has a low albedo, and it absorbs a lot of it. So let's look at that. If you have an increase in temperature, sea ice melts, leads to more open, dark water, more absorption of heat, more melting of sea ice, even more dark, open water, more heat absorbed, sea ice melts. Get it? This is a negative, in this case, this is a positive feedback loop. And it's positive because it is reinforcing. You should know that by now. That's a very key term in this course. A positive feedback. Ice melts, more dark open water, more heat absorbed, more ice melts, more open water, more heat absorbed, more ice melts. Here's an image looking at the Arctic Ocean The more ice there is, notice the more bouncing back to space of light, right? Now, if you have less ice, more dark open water, lower albedo, lower reflectivity. That's the basic idea here. And here's looking at ice loss from 1980 all the way to 2022. And you might say, well, look at this. It's gotten better. 2022, 2021 have been less bad than 2020, 2019, 2018, 17, 16, 15, 14. True, but look at the trend. That's what you need to focus on. And the trend has been at roughly 12% decrease per decade. So that's significant. Again, remember, September is the month with the least coverage of ice over the Arctic Ocean. Here's examples of 2007 versus 2017. The pink line is where the ice should be. Notice how it's the same on this image as it is in this image. So the pink represents the median, where it should be. Notice what happened in 2007 and what happened in 2012. There's a video that you can look at. Summer Greenland ice melt. So notice again, this is comparing the median, 1981 to 2010, the highest, and 2021. I couldn't get the updated version of this. This is something that's changing, and this is the idea of ice age. So basically, what's happening is the majority of the ice that you find in the Arctic Ocean now is either first or second year ice. The old ice that would remain in place year after year after year has gone from a significant amount in the 1980s to very little in the early 2020s. And the majority of the ice that you find is either first year ice and second year ice. So the median thickness has decreased, multi-year ice has also decreased, and the total mass is decreasing. So all those things are bad. This is a dated image, and they have not put up a new one yet. But it pretty much gets the point across as well. If you were walking on the Arctic Ocean in 1980, the average thickness of the ice would be around 12 foot thick. Now it is basically about 6. So the ice is thinning. And if the ice is thinning, it is more subject to storms and wind and currents breaking it up. Okay? Ice shelves. So these are floating ice that extends seaward from glaciers and land. Sea ice can be a few meters thick, but ice shelves can be hundreds of meters thick. If ice shelves melt, they do not raise sea level because they're already on the ocean. Okay? And shelves help to let me say that again. Shelves help to push the ice that's inland from coming out into the ocean, which would then increase sea level because you're going from land to the water. That ice can actually increase sea level. And here's an example. Melt days in Antarctica. So not as many. Antarctica is a lot colder, Antarctica is a lot more stable than Greenland, but that's still being researched. There's a lot more research about Greenland than there is Antarctica. So stay tuned for that. And here's a Greenland melt extent in 2022. 2022 being the red line. The 1981-2010 average would be the blue dashed line. And for the most part, the red is above the blue. Not always, but for the most part. So let's look at ice shelves that have broken up recently. In the Antarctic Peninsula, you had that one in 89, Larsen A in 95, Larsen B in 2002, the Wilkins one in 2008, and a partial collapse of Larsen C in 2017. So here's the Antarctic Peninsula. Here you have Larsen A, Larsen B, Larsen C, Wilkins. And this hook would be this, right there. There are other bigger ice shelves, the biggest of which is the Ross. And all this ice is on top of the ocean, holding back this ice from making it into the ocean. So they function as that buttressing mechanism. So again, there's a closer look, 89, 2002 on the left. It literally just, this used to be all of this, and then it just broke up into literally billions of icebergs. Here's Larsen C, and for reference, it's about the size of Delaware. So it's a big chunk of ice. Big chunk of ice. Once it all breaks apart, then it can just basically float away. It is at the mercy of the currents, and it breaks up into lots and lots of icebergs, and it's a danger to shipping, basically. And again, this crack is basically what this aircraft is flying over. Now, again, area about the size of Delaware. Its thickness is about 325 meters from top to bottom. Remember, the majority of this ice is below the water. And again, breaking off into billions of icebergs, which don't necessarily add to climate, to sea level rise, right? Because this is already on the ocean. But if you remove, let's go back to this image here, as you begin to take away a lot of the shelves like this one or any of these, you're taking away that mechanism that holds the ice back. Because any ice that melts and comes from land can add to sea level. Ice that's already on the ocean doesn't, because it's already there. Okay, so that's the whole idea here. So that's the presentation. Pretty straightforward, actually, but you need to have a good understanding of how all those other subjects like feedbacks and forcings and all that, how they link into what we're talking about now. If you have any questions, let me know. Come to the study hour, send me an email, whatever works for you. Otherwise, I hope you're doing well, and I will talk to you soon. Bye.